Otherwise, I will start.
Okay, sir. Okay, so we are starting our first session today. Professor Sharma sir is already here, and we will continue from yesterday. He said that we will start hypothesis testing today. So it is a very important topic for everyone. It is the fundamental of statistics. It is used in every single, be it any kind of research problem. So hopefully you will enjoy the lecture, and he always teaches in a very friendly manner. So please, sir, please start now.
Okay, thank you, Dr. Faz.
Sir.
And I would also like to thank Professor Akil Ahmed, the coordinator of this program. He
Yes, sir.
has really put in a lot of efforts to organize and as well as to arrange speakers from different parts. It's
Yes,
not
sir.
an easy job. And
Yes.
all right,
Yes,
so
sir.
I'll
All
share
right,
the
sir. Please start.
presentation and then we'll start. Okay. Is my desktop
Okay.
visible
Yes,
now?
sir. It's visible now.
Okay.
Okay.
So good morning to all the participants once again. And today our topic is most important. That is estimation and testing of hypothesis. And this is also called the backbone of statistics. Because we generally take a sample from the population, and the entire idea about the population is to be given based on the sample. So there are few problems in estimation and testing. Before we move on to the actual testing problem, you need to understand certain basics, and those basics are very important. For example, what is hypothesis? First of all, what is null hypothesis, alternative hypothesis? What do you mean by estimation? What do you mean by testing, right? What is the meaning of type 1 and type 2 error? So all these things I'll clarify in half an hour, and then we will move on to the practical examples of the first part, which is called the parametric test. Okay, let me open the presentation and start with the proceedings. So this part we have already covered. We just move on to estimation and testing straight away. Correlation part we have already covered. And let's now, this is the part which we have to cover today. Okay. So hopefully the slide is visible. This slide is visible.
Yes, sir.
Okay. So now if you see, this is estimation and testing of hypotheses. Those are the three words basically. One is called estimation, another is called testing, and the third is called hypothesis. So I'll explain you the meaning of all the three. First of all, and I will just discuss the parametric test. Parametric tests are applicable when your data satisfies certain set of assumptions like normality, independence, constant variance, etc. Right? Then the parametric tests are applicable, and somebody else will cover the non-parametric part where the assumptions gets violated, and then rather than applying parametric test, you have to apply non-parametric test. Okay. So first of all, we go through what is called estimation. Let's see. These are called test of significance. See, there is always some kind of population. Whenever we plan a study, we have to plan on certain population. But population is generally very large. We cannot study the entire population. Then what we do? We take a sample out of this population. Now, generally we take a random sample. Not always, but generally we take a random sample. Random sample, make sure one important point that every member of the population has the same chance of being selected in the sample. That every member of the population, if you take from the every unit you take from the population, that has the same chance. What does this mean? This means that there should not be any favoritism, there should not be any biasness in selecting the sample. That's why we usually adopt the technique of random sample. And there are number of sampling techniques which are random sampling, simple random sampling with replacement, simple random sampling without replacement, stratified sampling, cluster sampling, probability proportional to size sampling. So all these samplings are random samplings. Then there are known probability sampling also, like quota sampling, purposive sampling, judgment sampling, snowball sampling. So all these samplings are known probability sampling. Sometimes they are useful. For example, if I want to buy apples, then I do not go for the random sampling. I'll just go for the judgment sampling, because I'll pick up, let's say, 1 kg of apples. Then based on my judgment, I'll inspect each and every piece and then go for the selection whether I should go or not. So that is the judgment sampling. So known probability samplings are also sometimes important, but as far as the study, most of the studies are concerned, we use the random sampling techniques. Okay. Now there are two things here. One is a population, which is difficult to study. Then we take a sample out of this population, and generally a random sample. Now there are values which are concerned with the population. If your values, please try to understand, if your values are concerned with the population, they are known as parameters. For example, there are certain standard notations in statistics, like mean, population mean. Population mean we always denote by mu. Please remember this notation. Most of the time we denoted this population mean by mu. Then population variance, we denoted by sigma square. Yesterday I explained you right in the first lecture. Then population proportion, capital P. Proportion means what is the proportion of male and female in the entire population, right? Now we are not going to study the entire population. So obviously these parameters will be unknown to you. They are not known to you. Then we take a sample out of this population by using an appropriate sampling techniques, right? Let's say I take a sample of 500 people. Now X1, X2, X500, all these observations are known to you. So based on these observations, you can compute your sample mean. This is a population mean. Please remember, there is a difference between sample mean and population. Sample mean is which you can compute. Population mean which you have to estimate basically, right? So sample mean, let's say I have a 500 observations. So I'll add 500 observation, divide by 500, you will get sample mean, which is denoted by X bar. Similarly, you can compute sample variance, S square. You can compute sample proportion. In 500 observation, you can easily come out with how many males are there, how many females are there, and proportion of that, right? Proportion of males, let's say 60% females, 40% males. So you can easily come out. That is called small p. Now, here is an important point. We take out a sample from the population in such a way so that it should represent the entire population. It should represent the entire population. That's why there are different kind of sampling techniques. If your population is more or less homogeneous in nature, we can go for simple random sampling with or without replacement. If population is heterogeneous in nature, yesterday somebody was asking about the strata. So we go for the stratified random sampling. If stratas are of unequal size, we go for probability proportional to size sampling. So there are many sampling techniques. Because I will not discuss sampling techniques, that is not my topic. But anyhow, the idea should be clear that whenever we take a sample out of the population, then we use an appropriate sampling technique. Not only the appropriate sampling technique, but we also take out the appropriate sample size. Now somebody may ask, what should be the sample size? It's not a straightforward answer question. You cannot answer like this, because I generally conduct 2 days of workshop for medical doctors only on sample size, right? There are more than 200 formulas to compute sample size in different situations. So we have to see what is your design, which kind of problem you are tackling. Is it based on the testing of means or the testing of proportions, or based on ANOVA or something? So many things have to be checked in before computing the sample size. Okay. All right. Now we have taken a sample from the population. So there are two types of values. One is based, which you have computed based on the sample, X bar, population variance, S square, population proportion, small p. So if your values are based on the sample, that is called statistic, basically. So X bar is a statistic, S square is a statistics, small p is a statistics. So if you have used the appropriate sampling technique, you have the appropriate sample size, then what you will expect? You will expect that this sample mean will give you an estimate of this population mean. Sample variance will give you an estimate of the population variance. Sample proportion, which is small p, will give you an estimate of the population proportion, which is capital. So basically, our aim is to estimate the parameters of the population based on the sample. And this problem, that means we are referring back from the sample to the population, is called what is called estimation or statistical estimation. So that is the first word in estimation and testing. Hopefully it is clear to you, right? So this is what do you mean by estimation. Now, next problem. Once we estimate the parameters, now if you haven't used the appropriate sample size, your sampling technique is not good, then next problem comes, your estimates may be good or bad, right? Now question is, how good your estimates are. They may be good estimates, they may be bad estimates. That's why we go for the testing. So here comes the problem of testing. Now, before coming to the testing part, we should know what we want to test. That's why we frame the hypothesis first. So I'm giving you explanation of each and every word, estimation and testing of hypothesis. So first we estimate, then our problem is whether these estimates are good or bad. Now we have to go for the testing. And before testing, we need to plan what we want to test. And for that, we require hypothesis. So these are the certain learning objectives which we'll go through to understand the role of significant test, to distinguish between null and alternative hypothesis, to interpret p-value, and type 1 and type 2 errors. Okay, now here comes what do you mean by hypothesis. Now some people say there is a negative hypothesis, there is a positive hypothesis. Let me tell you, there is no concept of negative and positive hypothesis in statistics. And hypothesis, what do you mean by hypothesis? Here is the statement. A tentative statement regarding the population, not regarding the sample, please. A tentative statement regarding the population relating to a certain phenomena. Relating to a certain phenomena means relating to height, relating to weight, relating to IQ, relating to BMI, whatever. So a tentative statement regarding the population relating to a certain phenomena in which the researcher is interested. You may be interested in testing IQ level of certain people. You may be interested in testing mean weight of certain group of people, right? In which the researcher is interested and wants to verify on the basis of the sample. So simple idea of hypothesis is, if you have planned certain study and if you're able to frame the objectives of your study into 1 or 2 sentences, that becomes your hypothesis. Let me just explain. If you're able to frame the objectives of your study into 1 or 2 sentences, that basically becomes your hypothesis. Now there are 2 types of hypothesis. One is called the null hypothesis. Another one is called the alternative hypothesis. Now, how to frame null and alternative hypothesis depend upon your research problem. It depends upon your research problem. So I'll give you a few examples. So testing of hypothesis, please remember null hypothesis is always denoted by H0. H0 people also called or H0. Alternative hypothesis, you can use 2 notations. Either you can use HA, A stands for alternative, or people also call this H1. Because 0 is here, so people also call alternative hypothesis as H1, right? So that is the standard notation in most of the books, that H0 stands for null hypothesis, H1 or HA stands for alternative hypothesis. So I'll go to the next. I'll explain you everything with examples. Let's say how to frame the null hypothesis or the alternative hypothesis. Very important. Let's say somebody is interested in testing that I want to test the mean IQ of this population. Population is very good, people are very good, and or let's say about students. And he says that students are good, and I can expect that mean IQ of these students are likely to be about 100. So that is his claim, his or her claim, right? So we will frame the hypothesis. Now, what is the parameter of mean in the population? Mu. So I'll frame the null hypothesis H0, that mu is equal to mu naught, where mu naught is specified and it is given to be 100. So that becomes your null hypothesis. Whatever we want to test, is always put under H naught. And please remember, under H naught, there is always equal to sign. There is always equal to sign. So what we are testing here, that the mean IQ of a population is equal to 100, basically. So H naught is parameter of the population in mean is mu. So we will frame the hypothesis mu is equal to 100. If somebody is interested in testing that the variance of this population is equal to 5, then your null hypothesis will change. Then you will write H naught, not the parameter of the variance is sigma square. So your hypothesis will become sigma square equal to 5. Right? Similarly, if somebody is interested in testing that 60% of this population is likely to vote for this party, then your hypothesis will change. You will write capital P, which is a proportion, capital P parameter in the population, right? Capital P is equal to 0.60, 60%. All right. So it depending upon the problem. Sometimes we are testing the difference in two populations. Let's say difference in convent school and the government school, whether they are performing equally well or there is a difference. If they are performing equally well, let's say population parameter of the convent is mu1, that of the government is mu2. So I will write down the null hypothesis that under H naught, that mu1 is equal to mu2, that the performance of government and convent school they are same. So H naught will be mu1 is equal to mu2. So depending upon the problem, you have to frame your, first of all, the null hypothesis. Hopefully the null hypothesis is clear. Now corresponding to this null hypothesis, there are number of alternative hypotheses. Null hypothesis is always one. There could be number of alternative hypotheses. For example, if I am framing the null hypothesis that I want to test mean IQ of this population is equal to 100. Now it may not be 100. It may be greater than 100. It could be less than 100. I don't have any idea in the population, right? Now, if you don't have any idea in the population, then we take the alternative hypothesis, H1 or HA, that mu is not equal to 100. Mu not equal to mu naught means where mu naught is 100. So you can say mu not equal to 100. Now, if I'm writing the alternative as mu not equal to 100, then I'm not sure whether mu is less than 100 or mu is greater than 100. No idea. That's why this type of alternative is called two-sided alternative. Why two-sided? Because I'm not sure whether it is less or it is more. All right. But there are certain problems or some prior information is there that these are very good students, and I can bet, I am 100% sure that mean IQ of this population will be more than 100. Right? So if somebody is 100% sure, then we use one-sided alternative. So if somebody is 100% sure that these are very good students, the mean IQ of this will be, I'm sure, more than 100. So under H naught, I'll write mu is equal to 100, and alternative will change to this, that mu is greater than 100. Now greater than 100 means it becomes one-sided, right? Similarly, if somebody says that these are very dull students, I know their mean IQ cannot be 100. It is definitely going to be less than 100. If that is the case, then alternative will again change. Alternative, I'll write mu less than 100. Now, this is also one-sided. This is also one-sided. So to distinguish between greater and less, in bracket we write one-sided. For greater means on the right-hand side. So we write right-tailed alternative. And here less than means left-hand side. So we write one-sided left-tailed alternative. Now in almost 85 to 90% of the cases, let me tell you, we use two-sided alternative. Why? Because what will happen in the population, we don't have any clue. One-sided is to be used only if somebody is 100% sure, right? Then we use one-sided. Otherwise, most of the time it is two-sided. So hopefully, how to frame the null hypothesis, how to frame the alternative hypothesis is clear to you. Now, we are testing null hypothesis against one of the three alternatives. There are three alternatives. One is not equal to, other one is greater than, other one is less than. I have put or. So depending upon your research problem, either you are testing H naught versus H1 which is two-sided, or you are testing H0 versus H1 one-sided right tail, or you are testing H0 versus H1 one-sided left tail. You are not testing all the three alternatives. Depending upon your search problem, you are basically testing H0 versus H1. Now, H1 will depend upon whether it is two-sided, one-sided right tail or one-sided left tail. Basically, you are testing H0 versus H1. So remember this thing, please. So with this background, how to frame null and alternative hypothesis, let's move on to the type 1 and type 2 errors. What do you mean by type 1 and type 2 errors? See, what is written in the green line is most important. No study is perfect. There are always chances of errors. Let's say there is a basket with 100 oranges. Somebody is trying to sell me. And if I inspect one by one, let's say 1 or 2 pieces are likely to be bad. You cannot expect everything to be 100% correct, right? In any manufacturing process, if you take 100 shirts, 1 or 2 pieces may be bad, right? Now, question is, if no study is perfect, there are always chances of errors. In statistics, we always talk in terms of 2 different types of errors. One is called type 1 error, another is called type 2 error. And people get confused between type 1 and type 2 errors. Now, you know what is null hypothesis, you know what is alternative hypothesis. So here is the decision. And here is whether it is true or it is false. True means a good lot, false means the bad lot. You can understand like this. So what is type 1 error? Type 1 error is reject H0 when H0 is true. That means something is of good quality, but it has been rejected. Let me just repeat. Something is of good quality, but it has been rejected. This type of error is called type 1 error. And this type of error generally happens in many situations, particularly during selection procedures. In selection procedure, there are good candidates, there are bad candidates. Sometimes the good candidates are being rejected. The candidate was good, H0 is true, but it is being rejected because the second person is having pull or push, right? So then you commit type 1 error, and then the university has to, or the college has to suffer for how many years? 30 to 35 years. Deadwood planted for 35 years. And there are many samples in the university and colleges like that. You must have also seen. So this is called type 1 error, right? So type 1 error is very, very important. Reject H0 when H0 is true. Something is of good quality, but it has been rejected. That is type 1 error. What is type 2 error? Type 2 error is accept H0 when H0 is false. Something is of bad quality and you are going to accept that. That is called type 2 error. Let's say I want to buy apples and there are bulk of apples lying over there and I can see they are not of good quality. But the owner of the apple, he says, sir, you have to take only half kg or 1 kg. So you can pick or choose. So I make some judgment sampling, pick or choose, and bring them 1 kg home, consume them. And I got food poisoning. And in my family also, 2-3 people get food poisoning. And the entire family has to go to the hospital. And they charge just 10,000 rupees. Whose loss is this? It's our loss. That's why this error is even much more serious, right? So because you are going to consume that, accept H0, you accepted a bad lot. You accepted a bad lot. That is called type 2 error, right? So these diagonals, basically this is type 1 and type 2 error. What should have been the correct decision? Reject H0 when H0 is false. Something is of bad quality and you also rejected that. That's the correct decision. Look at this one also. Accept H0 when H0 is true. Something is of good quality and you also accepted that. That's the correct decision. So these diagonals, basically type 1 and type 2 errors. Now in economics, type 1 error is basically called producer's risk. And type 2 error is called consumer's risk. And if you ask any economist, consumer's risk is more serious than producer's risk. That's why people say type 2 error is more serious than type 1 error. Of course, both of them are serious, but I'll give you certain examples. Okay. Now, in economics, this is called type 1 error. Somebody is producing good items, but it has been rejected. That's producer's risk. Consumer's risk, you have accepted a bad lot. That's your risk. So type 2 error. So with this background of type 1, now these are errors. They are likely to occur. You cannot avoid them. Obviously, we want these errors to be small. We want these errors to be small. So that's why I'll give you certain examples of type 1 and type 2 error. Let's say look at the medical test from medical point of view, epidemiological studies. What is type 1 error? Type 1 error is also called a false positive. What do you mean by this? The person doesn't have a disease, but the test says they do have. Now, what does this mean? Let's say person is not having COVID-19, but when the test was done, it says the person is having COVID-19. So where this person will go? He will put into the hospital with another COVID-19 people and he will develop COVID-19. Right? You follow my coronavirus, he will get unnecessarily because that was a false positive. The person does not have the disease, but the test says they do have. Very serious error. And you can very well imagine this error happens number of times during the last 1.5 years. I'm working with the doctors, lot of doctors, and if I tell you the real situation, you cannot even imagine that type 1 error was more than 30% there. You cannot think of even, because in the initial stages, the test was not developed properly, but now it is. There is very, very less error now, right? Then what is type 2 error? A false negative. The person has the disease, but the test doesn't pick it up. The person was having COVID-19, coronavirus. When the test was conducted, it says it doesn't have. He come back home, there are 5 people in the family, all of them get infected. Very serious error because of one person. That is false negative. That's a type 2 error. So very, very important. Type 1 error is false positive. Type 2 error is false negative. Look at the court example. Convicting an innocent person. Person doesn't have done any crime, but he has been convicted by the judge. Very serious error. Convicting an innocent person. Not convicting the guilty is much more serious, because the person has done a crime and the judge has let him go and he may kill a lot of the other people also later on. So not convicting the guilty is type 2 error. So these are some of the examples in medical test and court examples, right? Then comes what is called the level of significance. Now, level of significance, alpha. Yesterday, somebody was asking why to take 0.05, why to take 0.01. So I'm coming to that point. Please try to understand. So here is, let me see. Now you can see, alpha is called level of significance. Now there are type 1 and type 2 errors. If you look at probability of type 1 error, that is called alpha. And we need to fix this alpha right in the beginning, even before conducting the experiment. I'm making a very strong point. We need to fix this alpha even before conducting the experiment. That is in your hand, level of significance. Now, when we talk about, now why it is called level? Because in statistics, generally we take 2 types of levels, 0.01 and 0.05. What is the meaning actually? 0.05 means, let's say if there are 100 items, if 1 or 2 are of bad quality, still I'll accept that lot, but there should be some limit. So maximum allowable error in general manufacturing process, is basically 5%. That means even up to 5 are of bad quality, still I can accept that lot. That's why we use the word level. You cannot go beyond this level. So we write alpha. Alpha is nothing but the level of significance. The smaller this error, better will be. If your experiment is very sensitive, you cannot afford 5%. Then you have to take alpha to be very, very small. For example, if your experiment is about testing of the aeroplanes, and there you take alpha to be 0.05. What does this mean? This means that if 100 aeroplanes will fly, 5 of them are likely to fall. Who will sit in the aeroplane next day? Nobody will sit in the aeroplane. So there you need to fix this error to be very, very small. Maybe 1 in 1 lakh, maybe 1 in 2 lakh. Very small, right? So this is what we mean by level. So in general manufacturing process, generally we talk alpha is 0.05 or 0.01. 0.01 means if out of 100, one item is of bad quality, still you can accept that lot. but there should be limits. So maximum allowable error is about 5%. Okay, so this is what we mean by level of significance. Then probability of type 1 error is alpha, probability of type 2 error is called beta, and probability of type 2 error is important in the sense because from probability of type 2 error we compute what is called the power of the test. What is called the power of the test, and power of the test basically depends upon beta, your sample size. They are directly proportional, right? So for any test, whatever we want to make in statistics, there is an associated power, and if the power of the test is very less, let's say I take a sample of size 6-7 people and make the conclusion about the entire population, and you submit your paper and the referees ask you, you compute what is the power of your test, and then you compute the power. There is a power for each and every test, a t test, ANOVA, you can compute power, and then power is coming out to be 40%. Do you think with 40% power you can make conclusion about the entire population? No. So minimum power required is about 80%. It should be more than 80 or 80% minimum, right? So this type 2 error help you to compute power of the test, and 1 minus the probability of type 2 error will give you power. Then we come to p-value. Now p-value, people get confused with p-value, and in many of the books in statistics, p-value is not explained in a proper way. When I was reading this definition, this is the definition I have gone through. I could not understand what it is. Maybe you will not be. Probability of getting a sample results as extreme as those obtained under the assumption that the null hypothesis is true. Even I could not understand this definition. Then because of my experience, I have written a book also on medical statistics. I have given a very simplified definition of p-value, which I'll tell you. But for the time being, you please remember, actually p-value is nothing but the actual level of significance. You actually compute and reject the null hypothesis. You remember this word, please. Alpha is fixed in advance. Let's say alpha is 0.05. Reject the null hypothesis. Rejection or acceptance is always for null hypothesis, not for alternative. Please remember this thing, right? And somebody is asking type 1 and type 2 error. I'll answer that. I'll give you time. Okay. And reject the null hypothesis if p-value is less than. So you should understand what do you mean by p-value. Just wait for a moment. I'll come to this. For the time being, remember, we reject null hypothesis when p-value is less than alpha. Alpha is fixed in advance. It could be 0.01, it could be 0.05, or maybe some 0.02, doesn't matter. Okay, and we need to compute p-value. Let's come to the definition of p-value. Now you see what is written in the red line at the top. P-value is nothing but area outside the computed value. For any test you are going to compute, there will be a computed value. And there will be for any distribution, whether it is chi-square, whether it is normal distribution, whether it is t-test, there is a curve, and that is called t-distribution curve or normal curve or the chi-square distribution or the F distribution. There is a curve. And what is p-value? You have a computed value, you compute the value of the test statistics, and depending upon whether your hypothesis is one-sided or two-sided, if it is two-sided, then it will be area outside the computed value on both the sides, right? And if it is only one-sided, then it will be entire area on the either right side or on the left side. So I'll just give you a simple definition from a normal point of view. Let's say you are testing a normal distribution, and this is the graph of a normal curve. Everybody knows that. It is symmetrical. Symmetrical means area on the left-hand side is same as area on the right-hand side. Now, suppose I choose alpha to be 0.05. That is in my choice, right? Then if you look at the standard normal tables, any standard normal tables, let's say I'm testing H0, mu is equal to mu naught against the alternative that mu is not equal to mu naught, and taking alpha to be 0.05. Now, if I'm saying mu not equal to mu naught, it is two-sided alternative. then this is called, alpha is basically called critical region. That means probability of rejection, which is probability of type 1 error, right? So obviously this rejection will be, because it is two-sided alternative, so it will be equally distributed on both sides. I don't know whether it is on the left-hand side or it is on the right-hand side. So I equally distribute. So equal of 0.05, I divide by 2, or 5% divided by 2 will be 2.5. So it will be 2.5 on this side and 2.5% on this side, right? Now, if you look at the standard normal table, it's a two-way table. If you know the probability, you can compute point. And if I know the point, you can compute probability, right? So let's say I know the probability, that probability of this region, which is the green region I marked, which is also called the rejection region, is 0.025. And the entire region probability is 1. So if you look at the standard normal tables, up to this, up to half, it will be 0.5. So if I subtract 0.5 minus 0.025, I'll get 0.475. And now, if you know the probability, then you can compute the point. And if you look at the standard normal table, your point will come out to be 1.96, right? And what is p-value? P-value will be area outside this value. So area outside this will be 1.96. And on the left hand side, there is no need to compute because this is metrical. So on this side, it will be minus 1.96. And area outside is a rejection region. Area outside is a rejection region. So if your, let's say your computed value is exactly equal to 1.96. If your computed value is exactly equal to 1.96, then what will be your p-value? It is area outside this. So area outside will be 1.96 on the right hand side, 0.025, on the left hand side again 0.025. So your p-value will come out to be exactly 0.05, right? So for alpha, here I have written everything. For alpha is equal to this. The critical points are denoted by this and this. The area outside this and this is 0.5. Therefore, if your computed value for two-sided alternative is exactly equal to 1.96, exactly equal to 1.96, then your p-value will be exactly equal to 0.05. But do you think every time you will get 1.96? You compute your value, it will be something else. Let's say it is more than that. Suppose it is 2.76. Now 2.76 will lie somewhere here. It is 1.96. 2.76 will be somewhere here. And on the other side, it will be minus 2.76. So, and what is p-value? P-value will be area outside this, your computed value. So your p-value will become small because area will be small then. You can read green area will become small, right? Green area will become small. So your p-value will be less. So when your value of the test statistics becomes higher, p-value will become small. And when the p-value will become small, it will definitely fall into this green region. And that is called rejection region. So you will reject your hypothesis. Other way around, this white region is basically acceptance region. This green region is a rejection region. Let's say my computed value is 1.25. So 1.25 will come somewhere here. It is less than 1.96. Then what is p-value? Area outside this. So your p-value will increase. Your p-value will be more than 0.05. And once it is crossing more than 0.05, you are going into acceptance region. So there is no need to see the statistical tables. There is always an inverse relationship between p-value and the test statistics value. If your test statistics value becomes more, definitely your p-value will become small. And if your test statistics value, computed value is coming out to be less, then your p-value, which is area outside, will become more. And when to reject? Simple idea is, if your p-value is more, you cannot reject. You have to accept H0. If p-value is small, you have to reject because it is going into rejection region. So that is the idea of this p-value. So there is always an inverse relationship between computed value and p-value. If computed value is large, p-value will be small. And if it becomes this, we reject H0 because it is definitely going into rejection region. And if computed value is small, then p-value will be large. right? So there is an inverse relationship. Smaller the p-value, greater is the evidence against null hypothesis. Obviously, smaller the p-value, greater will be evidence, because smaller the p, it will definitely going into green region. You can say green region is up to a 0.05. So if p-value is less than 0.05, you are sure that it is going into rejection region. That's why I write here, reject H0 if p-value is less than alpha. Okay, so that is the idea of p-value. Now we are coming to what is called parametric test. I'll cover only the parametric test and try to give you, because we are left with half an hour to 35 minutes. At 10:15, I'll be covering this entire topic. So in parametric test, the most important assumption is of normality. And normality can be tested with the help of graphical procedures. So you can note down there are 3 graphical procedures. One of them is called histogram. You look at the shape of the histogram. If it is approximately symmetrical, then your data is following a normal distribution. Number 2, you can go for the box plot. Yesterday I explained you box plot. If median is there in the center of the box, your data is approximately normally distributed. The third important plot is called QQ plot. That is called normal quantile plot, or sometimes people also use normal probability plot. So normal quantile plot, with the help of normal quantile plot, you can also check the normality of the data. So these are 3 graphical procedures to check the normality of the data, and very important graphical procedures. Let me just repeat: histogram, box plot, QQ plot. Then there are exact procedures also. These are called non-parametric procedures. One of them is called Sparrow-Wilk test. Sparrow-Wilk test. Another one is called KS test, Kolmogorov-Seminole test. So these tests are also in SPSS. I will show you. With the help of these tests, you can check the normality of the data. Now, in parametric test, the most important part is observation must be independent. Your observation must come from normal distribution. The hypothesis involve population parameters. That means your hypothesis must reflect some population parameter. It could be mu is equal to mu naught. It could be sigma square equal to sigma naught square. It could be capital P is equal to P naught, something like that, right? Okay. Now, there are 2 types of tests in parametric: large sample test, small sample test. For large samples, generally we use what is called Z statistics, which is generally used in large samples. Testing of proportions, testing of means. But there are certain restrictions of that statistics, that the population variance must be known to you, which is generally unknown, right? But in most of the statistical packages, particularly in SPSS, the Z test is not given. Only T test is given. Let me tell you the reason. Because T test we generally use for small samples. Small sample means 10, 15, up to 30. Less than 30 is considered to be a smaller sample. All right. Now, of course, depending upon the problem, it's not always less than 30. Suppose you have 10 lakh population, you cannot take a sample of size 30 then, right? Okay. Now, actually what happens, this T test approaches to Z test. It's approximately same. Whether you apply Z test or you T test, whenever your sample size is sufficiently large. So that's why T test is applicable to the small samples, and it approaches to Z test when your sample size becomes sufficiently large. So that means T test is applicable to small sample as well as large samples, basically. So that's why in many statistical packages, only T test is given. Because when sample size becomes large, it approaches to Z test, right? Now, where this T test is applicable in many situations. So we'll not discuss Z test here, we'll just discuss T test. So T test is used in solving number of problems. Testing of single population mean. Somebody want to test that mean IQ of this population is equal to 100. In single population mean, some benchmark, some standard value you need to test, which will be given to you. So in this case, mean IQ is given 100. So I'll frame the hypothesis H0 mu is equal to 100, right? Or somebody is interested in testing that the mean weight of all the Aligarh Muslim University students is likely to be 60 kg. So I'll frame the hypothesis H0 that mu is equal to 60 kg. And that can be tested with the help of T test, provided the sample is following a normal distribution. We need to check. Then difference of two population means, as I already given you example of convent and government school, somebody wants to compare, or let's say you want to compare two different type of chemotherapies. One group of patients you give one type of chemotherapy, another group of patients you give another type of chemotherapy, and then you look at the recovery time, that is your response variable. So we want to check whether the recovery time of both the chemotherapies which are given, whether it is the same or there is a difference. So I'll frame the hypothesis H0 mu1 is equal to mu2, where mu1 is the recovery time of the patients receiving chemotherapy 1, mu2 receiving chemotherapy 2. So if their recovery times are same, and let's say I accept the hypothesis, then you can give any type of chemotherapy, but you have to be careful when we reject the hypothesis, which chemotherapy is better. So answer to this will be again given by t-test. So testing a single population mean, testing difference of population means. Difference means you can write mu1 minus mu2 is equal to 0, which is same as testing mu1 is equal to mu2. Then t-test is also used for paired data. Paired data means data is like this: before giving the treatment and after giving the treatment. Before giving the medicine and after giving the medicine. So if your medicine is effective, then obviously before and after should vary. Values should vary. So they are present in pairs. For that purpose, we also use pair t-test. Then yesterday I discussed about the correlation coefficient. We have the significant correlation, non-significant. That was also tested with the help of t-test. Then there is another parametric test which is called equality of two population variance. Equality of means is tested by using t-test. But if there is an equality of variance, let's say I want to test sigma 1 square equal to sigma 2 square. That can be written as sigma 1 square divided by sigma 2 square equal to 1. One and the same thing. Then that can be tested with the help of F statistic. Then there is one-way ANOVA, two-way ANOVA, multi-way ANOVA. All these are there, which also comes under what is called parametric test. So I will discuss with the help of examples. For example, if you are testing a single mean, hypothesis will look like this: mu is equal to mu naught, where mu naught will be given to you, just like IQ or mean weight. Difference of two population means mu1 is equal to mu2. Paired, in paired samples, mu d, which is called the mean difference before and after, is equal to 0. If I accept the hypothesis, that means the medicine is not effective, because before and after they are present in pairs, there is no difference in before and after. Then how medicine can be effective? So we are testing in the population that mu d stands for population mean difference, is equal to 0. So this has to be not equal to 0 basically, so that the medicine is effective or it is having worse effect. Then correlation coefficient is also tested with the help of t-test. With the help of F-test, you can test equality of variances. And then there is a chi-square test, which we test sigma square equal to sigma naught square, just like mu is equal to mu naught square. Then there is one-way, two-way, and all these things. Okay, so here I'll just discuss, and then we'll come to the practical demo of one-way, one sample, two sample independent t-test. Can we say that the mean weight of a certain population is different from 60 kg? So I'll frame the hypothesis mu is equal to 60 kg because mean parameter in the population is mu. So I'll write H0 mu is equal to 60 kg against mu not equal to 60 kg. One sample t-test, because I'll take a sample and test it. And what parameter I'll observe? Characteristic I'll observe? Weight. Similarly, does the mean weight differ in two regions? For example, can I say that there is a significant difference between the mean weights of Punjab and Haryana or UP and Haryana? So for that purpose, I'll use independent t-test, because these two regions are different regions. One is UP, another is Haryana. Then whether the medicine is effective in controlling blood pressure. So you have X values before giving the medicine. Let's say there are 20 patients. So they are coming to the doctor. Doctor examine their blood pressure, and you have 20 values: X1, X2, X20, without giving any medicine. Then doctor give them medicine. Then follow them after say 2 months. Now, so it's the same set of patients. They are not independent. So one value will be before giving the medicine of the blood pressure. Another will be after giving the medicine. So then you look at the differences. Let's say if all the differences are 0, that means you are accepting the hypothesis. That means you can immediately say medicine is not effective at all. But If they are not equal to 0, you are accepting the alternative, then obviously medicine will be effective, right? So that is called paired t-test because observations are present in pairs before and after. So I'll go for the practical demo of all this. There are formulas this is the formula which we use for one sample t-test. I mean, I take a sample of observation, compute its mean, then under H naught, mu is equal to mu naught will be specified. So I know the value of mu naught. And then I compute this variance of the sample observation, that is computed like this. And division factor is here, n minus 1. And you compute the value of this statistics. The denominator is basically called standard error, right? And this is having t distribution with n minus 1 degrees of freedom. Why n minus 1 degrees of freedom? Because degrees of freedom are nothing but number of independent observations which form FORM, which form the statistic minus the number of restrictions. Let me just repeat. Degrees of freedom are nothing but the number of independent observations which form FORM, which form the statistic minus the number of restrictions. So what is the restriction here? Basically, n observations are involved in computation of mean and variance. But one restriction is that we are subtracting x bar from every observation. So your degrees of freedom are reduced by 1, basically, right? Or you look at the division factor 1 over n minus 1. That also sometimes determine the degrees of freedom. So degrees of freedom is n minus 1. So this is the formula which we use for one sample t-test. This is the formula which we use for two sample t-test. I take an independent sample from government school, another sample from the convent school, compute their means, compute their variances S1 square, S2 square combined by using this formula, substitute here, you will get another t value. And degrees of freedom here will be, for first sample, it will be n1 minus 1, n1 number of observations from first sample, n2 from second. So total number of degrees of freedom will be n1 minus 1 plus n2 minus 1, n1 plus n2 minus 2. And for pair t-test, we use this formula where di is nothing but the differences between before and after. So you will get a single number now, d1, d2, dn. Compute the mean of that, d bar, compute the standard deviation of that, and then substitute here. So that is a formula for t-test. So I'll give you a practical demo in next 5-6 minutes, and then we'll move on to one way ANOVA. Okay. So here is the practical demo of one sample and two sample problems in t-test. Let me open some data file. So there is a data file here. I'm just using one sample t-test. Just wait for a moment, it is just opening. Yeah. All right. Now problem is like this. Please, if you have carrying a pen or pencil, you can note down please how this problem is framed. There was a population and researchers like you was looking at this population and he realized that weight of the people, they are increasing. Then idea struck to his mind, why not look at their BMI level, right? So in medical sciences, BMI level is an indicator of overweight, obesity. That is called body mass index. How it is computed? It's weight in kg divided by height in meter, not in centimeter, height in meter square. That is the formula to compute BMI, right? So he has taken a sample from this population and computed the BMI level. So for example, the first person has a BMI of 23, 25, and so on, right? For example, this person has a BMI of 37. This is 39. Now, roughly, you can note down, please. Although cutoff point is 18.5, if it is less than 18.5, person is considered underweight. But I'll roughly take 20. Let's say if somebody's BMI level is less than 20, you can write down person is considered underweight. Less than 20, in front of this, you write down underweight. 20-25, that means between 20 to 25, the person's BMI is considered to be normal. a person is a normal person. Not overweight, not underweight, it's a normal person between 20 to 25. But if it is between 25 to 30, the person is considered to be overweight. You can write down. And if it is beyond 30, the person is considered to be obese. Right? Now, what is the question here? Question here is, he want to test whether this population has a tendency towards normal BMI level or they are having tendency towards obesity or overweight. That's the problem. Right? So if this population has a tendency towards normal, then BMI level should fall in the normal range. What is the normal range? 20 to 25. So you can take any value between 20 to 25 for testing. Let's say this is a mean BMI level I want to test. Yes, please. Any problem? His voice is coming? Dr. Faz? Yeah, everything is okay. I thought there is some. Okay. Now I will test this hypothesis. Normal BMI level is between 20 to 25. So you can take any 22.5, 23, whatever. And if I accept the hypothesis H0 that mu is equal to 23 or 24, then there is no need to instruct any people. I can say that, okay, these are having normal BMI levels. So sample of observation has been taken, mean has been computed, standard deviation has been computed, and all the values are put into formula. And then computed value will be there. And what is p-value? P-value will be area outside the computed value. And that will be given the p-value. You just need to check whether p is less than alpha or more. If p is less than alpha, reject. It is going into green region. If p becomes more than alpha, it is going into white region. Remember that figure. So we just look at p-value, right? So here is the test statistics. So let me frame the null hypothesis. You can write down, please, H0. Let me put this as mu is equal to 24. Against the alternative that mu is not equal to 24. Right? H0 and H1. Why I am taking 24? Because 24 lies between 20 and 24. 25, normal. Okay. Go to analysis. Go to compare means. Here is a one sample t-test. And in one sample t-test, you look at BMI. And our test value is mu is equal to mu naught. That's why under H0, there is always equal to sign. So I need to specify what is under H0. 24. Right? And now you will get t value and p value by using that formula. So press OK and you will get the answer. That is one sample t-test. There are 25 sample observations. Mean is this much. Standard deviation is this much. Then what is the standard error of mean? Standard error of mean is nothing but standard deviation divided by under root of n. Under root of 25 will be 5. So if you divide 7.003 divide by 5, you will get standard error of mean, which is 1.401. And what is t value? T value is nothing but this mean minus this value. X bar is 34.04 minus 24 that we want to test. Divide this by standard error. So you compute 34.04 minus 24 divide by 1.401. You will get this t value as 5.027. And how many observations are there? 25. So degree of freedom will be one less. So 24. And this is your p value. Please remember, p value is never 0. I can show it. Let me just click here. If you click this and then right click, and then let's look at the cell properties. And in cell properties, look at numbers and decimals. I increase to, let's say, 13. Instead of 3, I increase this to 13 and press OK. Now you can see p value is never 0. Actually, the p value is this much. Right? So p value never touches the x-axis actually. So p value is never 0. If it is written in SPS, because it will give you up to 3 decimals, 0.000, you always put 1 at the end. So you write p value as 0.0001. Right? Okay. Then this is the p value. Certainly this p value is less than 0.05. If this is less than 0.05, you will reject H0. So H0 is rejected. That means If you are thinking that mean BMI level were 24, your claim was wrong. Now somebody may ask whether people are moving towards obesity or overweight. Yes, you can judge from here. Look at the sample mean. Your sample mean is 31.04. It is beyond 30, and beyond 30 means obesity. So definitely you can see that these people are not having normal BMI level. They are moving towards obesity. You have to instruct people, please don't eat pizza, burger, noodles. Your weight is increasing. Be careful, right? So this is what do you mean by the crux of this one sample t-test. So I completed one sample t-test. Now going back to two sample t-test. Let me open another file. Okay, so experiment is like this. There was an industrialist. He want to hire people for his industry. Then there were two types of groups. One type of group has done post-graduation. Another, they were undergraduates. And it is a semi-skilled kind of work. But one idea stuck to his mind. Let us test their IQ levels. IQ level of PG and UG group. PG means post-graduation, UG means undergraduates. Let's test their IQ levels. If their IQ levels are almost same, then you can very well understand he will hire people from UG group because he has to pay less salary. If he hire people from more educated, then he has to pay more salary, PG group. So to save his salary, he want to test this claim that the IQ levels of UG and PG, whether they are same or they are different. So null hypothesis is if the mean UG level in the population is, let's say, mu1 and that of the PG is mu2. So he want to test mu1 is equal to mu2. Against the alternative, mu1 is not equal to mu2. Now let's check whether his claim is true or not. So this is how the data is to be fed. First of all, IQ levels, and then you have people from PG. I just put 111 and you know how to label. You go to label 1 by PG, and after that you have the IQ levels of second group and you label that as UG, right? So this is how you have to feed the data. Now what is our hypothesis? You can write down please. H0, mu1 is equal to mu2. Alternative, mu1 is not equal to mu2. Okay, so formula you know. So here is, you will get t value and p value. Go to analysis, go to compare means, go to independent t-test, and your IQ levels, that is your test variable. And what is your grouping variable? Your grouping variable is groups. So I'll take it here. Define groups. We have only two groups, 1 and 2. Press continue. And in options, you don't need to click anything. That's all. So you have done with the two-way analysis. So it's very simple. You will get t value and p value. So here is the result. So PG group, this is mean IQ. UG group, this is mean IQ, standard deviation, standard error of mean. Then this is the t value. And why the degrees of freedom is 86? Because N1 minus 1 will be 26, 27 minus 1. N2 minus 1 will be 60. So 26 plus 60 will be 88. And this is your p value. So again, this p value is less than 0.05. So we will reject the hypothesis. We will reject the hypothesis. Which hypothesis? Null. Null hypothesis has to be rejected. What was the null hypothesis? Mu1 is equal to mu2. That the mean of PG and UG, they are same. But this was his claim. But it is being rejected. That means there is a difference between PG and UG IQ levels. Let's see which one is better. Look for the mean. The mean IQ level of PG is 95.4 and that of UG is only 79. So that means he was thinking that I will save money by hiring UG people from UG group. That claim is not true. So he has to hire only people from PG group because they are having higher IQ levels. So that is the crux of this problem, which we have tackled with the help of what is called two sample t-test. Okay. Now two sample t-test is over and let's move on to paired t-test. because you have lost 15 minutes in the morning, you came late, many of you. And then my time is given up to 10:15. So I'll wind up at 10:15. I don't know how far I can go, but anyhow, pair t-test we can easily compute. Pair t-test. So here is a pair t-test before and after situation. So these observations are before giving the treatment. These observations are after giving the treatment. So basically, then we'll compute the difference between before and after, and pair t-test is based on that, right? So if we reject the what is hypothesis here? Mu d is equal to 0, mu script d. That means the mean difference in before and after is equal to 0. And if I accept that hypothesis, then the medicine is not effective at all. And you can implement on yourself also. Let's say Dr. Faz design a performa where there are some questions related to statistics right in the beginning: skewness, kurtosis, mean, median, mode, correlation, regression, parametric test, etc. Right? And right in the beginning give you this test. That is, now you try to solve certain questions. That is a before score. After the entire program on 29th, the same performa is given to you again, same questionnaire. That is after you learned something. And then you again score. Which score will be better? If you have learned very well, after score will be better than before. But suppose before and after they are same. That means the program is not effective at all. So it can be used in number of situations, right? So go to analysis, go to compare means, go to paired t-test. And before and after you take it here and then press OK. It's very simple. And here is the answer. So just look at the t-value. This is the computed t-value. 20 pairs are there. So degree of freedom is 1 less, 19. And this is a p-value. P-value is 0.013. Again, this p-value is less than 0.05. That means H0 was mu d is equal to 0. It is rejected because p-value is less than 0.05. So that means the medicine is certainly effective. Your result is, conclusion is, medicine is certainly effective. So now this is what do you mean by all t-tests I completed, and the correlation was also tested by using this. Now I am left only with 7-8 minutes. And if you allow, then I can compute. I can go for one-way ANOVA, not two-way. Time is less. So Dr. Faz, I have 7-8 minutes.
Sir.
Can I go for one-way ANOVA at least?
Yes, sir. Sir,
Okay.
7-8 minutes are left.
Yeah. One-way ANOVA. So straight away I'll move on to one-way ANOVA because other speaker also have to join you from UK. Okay, so pair t-test. What is analysis of variance? I'll just take 2-3 minutes and then come to the straight away practical demo. Basically, one-way analysis of variance is an extension of t-test. T-test is used for comparing two groups, not more than two groups. But suppose there are 3 groups, there are 5 groups, there are 10 groups. I want to compare them. So in two groups, we compare mu1 is equal to mu2, PG and UG, or convent or government. But suppose there is third group also, mu1 is equal to mu2 is equal to mu3 is equal to mu4. 4 groups are there. Then they cannot be tested with the help of t-test. Then we move on to what is called ANOVA. And what is ANOVA? Analysis of variance is a technique which partition the total variation present among the set of observation into number of components. Now, this may not be very clear to you, but I'll give you a simple way of looking at analysis of variance. So if you look at one-way ANOVA, this type of hypothesis we have. Suppose we are testing k number of groups. So hypothesis will be mu1 is equal to mu2 is equal to mu3 is equal to mu k. So there is one-way ANOVA model, which we write mathematically in this form. Yij is called response. This mu is called overall general effect, which is beyond your control, and this is error. Yesterday I told you what do you mean by this error? Error in measurements generally, right? So okay, let me give you a simple example of one-way ANOVA. Suppose I'm looking for, I want to buy, let's say, tubes or bulbs, right? and there are different brands available in the market. There is a Philips, there is a Crompton, there is Sylvania, there is Bajaj. And whenever we go to the market to buy a specific brand, we have certain things in mind that I want to buy that brand which is having the maximum life length. Right? Now, suppose I take a number of brands and put them on test. I take 10 tubes from Philips, put them on test and note down their life length. So this Yij is the life length. Right? Yij is the life length. So, and this life length is affected by which kind of brand you are using. Either you are using Philips or you are using Crompton, you are using Bajaj. So K different brands. So basically I'm testing that alpha 1 is equal to alpha 2 is equal to alpha K. That the life length of all the brands is same. If the life length of all the brands is same and I accept this hypothesis by using certain statistical techniques, then you are safe. Your experiment is over. Go to market, buy any brand because life length of all the brands is same. But suppose I reject this hypothesis. Then two important questions are there. Which brands differ among themselves and which brand is the best? And answer to this is given by 1 by ANOVA. So this Yij here response, which is the life length, depends only on differences in brands. Error is beyond your control. Overall general effect we take because something which we cannot control. For example, I am sitting in Chandigarh, you are in Aligarh or in other places of India. I cannot say I am taking more oxygen than you. So the certain things which are beyond your control, right? So, okay. So you can understand from this diagram, I'm left with just 2-3 minutes more. Let's say these are, you take 10 tubes from Philips, put them on test. 1 stands for that they are coming from first number of brand, N1 number of tubes. They are coming from second brand, they are coming from kth brand. And the total number of tubes will be N is equal to N1 plus N2 plus Nk. Right? Now, if you see, these are coming from the same brand. These are from the same brands. So total variation present among the set of observation can be split up into two parts. One will be between the brands variation. Another will be within the same brand variation. Now, there will be variation between the brands because they are coming from different machines, different material, different people are operating. So that is likely to be more. So between variation is likely to be more rather than within variation. Within variation means they are using the same material, same machine, same person is operating. So this will be. That's why within is sometimes called error. And what is an also variance? An also variance split this total variation present among the set of observation into between variation and within variation. That is ANOVA, right? So here we get this type of table. Between variation will be given, within variation will be given, and then you will compute F value, and then you have to see whether your F value corresponding to this F value, you will get P value. And just see if P value is less than alpha, you reject. And if P value is more than alpha, you accept. If it is more than alpha, you accept. There is nothing to do. All the brands are same. You go to market, buy any brand. But if I reject the hypothesis, then we have to further test, which is called multiple comparison test. That is given by post hoc test. And that will give you the clear picture, which brand is better, which is at bottom. So you can put them in hierarchy. So I'll straight away go to the practical demo. I'm left with 2-3 minutes. So that at least up to 1 way ANOVA I can cover. Okay. This is the data for 1 way ANOVA. Just wait for a moment. So it will split the total variation into two parts, between and within. So I have taken few tubes from Bajaj, given this as 111 and put that in front of that Bajaj. Then after that, you have the life length from Philips. You have after that from Crompton and after that from Sylvania. So basically you can write down the hypothesis you are testing. Alpha 1 is equal to alpha 2 is equal to alpha 3 is equal to alpha 4. That means life length of all the brands is same. What should be the alternative? Alternative is at least two of them may differ. There may be differences in at least two. There may be three, there may be differences in four, all the four. But at least two of them. There may be differences in Bajaj and Philips or Bajaj and Crompton or something like that, right? So this is what we are testing. So go to an analysis, go to compare means. There is 1 way ANOVA. This is your dependent variable is Yij, that is the life length. These are your brands. And then you go for the post hoc also, because I don't know whether it will be, if it is rejected, I'll look for post hoc. If it is not, I'll not go for that. So generally people use Sheffield's test or Tukey's test, they will give you simple results, similar results. So in options, you must click on to descriptives and this means plot. Descriptives and means plots. Let's continue and then press OK. So here is the result. So finally, you have this table of one-way ANOVA. It just takes fraction of seconds to compute. Mean and SD table, but this is the main table. So you have 4 brands, so degrees of freedom will be 1 less. You have 37 observation, degree of freedom will be 1 less. So this is a between group variation, this is a within group variation, and this is your p-value. So this p-value is coming out to be less than 0.05. That means you will reject the hypothesis. That means the life length of the brands differ. Now, which ones differ? That further we have to see with the help of post hoc test. We have already applied. So first it is keeping Bajaj as fixed. So Bajaj compared with Philips. Look at its p-value. More than 0.05. So there is no difference between Bajaj and Philips. But look at Bajaj and Crompton. There is a difference because p-value is less than 0.05. Bajaj and Sylvania, no significant difference. So similarly, Bajaj is over, then it will fix Philips and compare with the rest of the 3. Then Crompton compare with that. This is very difficult to read. Better table is this. That is called homogeneous subsets. So what it does actually, it will club those brands into one group which are having similar life length, and those who are having very different, they will be put into another group. So here you can see the mean life length of Crompton is only 59. So, and mean life length of Sylvania, Bajaj and Philips is put into another group. That means there is no significant difference between them. So, but if you see, they are into one group, but which one is the best? Which is having the maximum life length? So maximum life length of Philips is 84. So 84, Bajaj is number 1, followed by, Philips is number 1, followed by Bajaj, which is at number 2, followed by Sylvania, which is, but there is hardly any difference. The worst is Crompton. So Crompton will be out, right? So this is how you can compare using one-way ANOVA. So I'll stop here because time is short. And if you have any questions, I think there is not even time for questions, but anyhow, if there is 1 or 2 questions, I can take up. Yes, please, Dr. Faz. Dr. Faz?
Sir, my voice is coming?
Yes. Yeah.
Okay. So one of them is asking that, can I compare 2 groups from independent experiments with different baseline readings by normalizing to the average of the controls of each experiment? Sir, I'll forward this to you.
Let me see. Because whatever he is saying,
So
can I
this was
compare
sent
2
to-
groups
yeah.
from independent experiments? Yes, you can compare with different baseline readings by normalizing to the average of the control. Yes, you can do that. Definitely you can do that. Yes, that is true. Yes, please. Any other question?
So one more was, if type 2 error is more critical than type 1 error, then for every experiment, we should have considered alpha to be probability of type 2 error.
He is a person not from statistics. We
Yeah.
cannot fix type 2 error. The problem in testing of hypothesis is we always fix type 1 error and try to minimize the type 2 error, basically. That is the procedure we have to follow. We cannot fix type 2 error, not at all. That is not possible.
So one more I have sent you.
Hmm.
This is a particular problem.
If X population under 2 different governments, A and B, and their violations the governments did on the population that led to an effect, which test will be used for analysis? Question is not very clear. X population under 2 groups. Okay, how many people are affected? He is asking basically. So we will apply Z test for proportions in this case. Z test for proportions will be applicable if you are testing about population, and there will be a proportion that X number of people are affected in population A, Y number of people are affected in population B, and you are testing the proportions. So Z test for proportions will be applicable. Yes, please. Any other?
So one more I've sent you. If two data sets has same distribution.
If the two data sets have the same distribution, which is normal distribution, but one gives us a distribution curve which is symmetrical, another is positively skewed. Yes, very important. Let's say one group is having your normally distributed, another is not. Please do not apply t-test. Then you have to go for the non-parametric test, which will be covered later. Yes, please. Any other question?
Okay. So that's it, sir.
That's it. So sorry,
Yes, sir.
that was a shortage of time. I would have covered the two-way, but anyhow, somebody else will cover two-way.
It's
So,
okay. It's okay, sir.
yeah.
So let us thank. You can send your messages directly to Sharma sir, and